Hey there, and welcome to your next lesson on Foundation Mathematics. So we're looking at the last topic we need to look at in algebra today, which is sequences. So a sequence is just, it's like a group of things with a particular order to it. So we have the first thing, the second thing, third thing. Those things could be numbers, could be a progression of numbers, or it could be shapes. Um, but that's basically what a sequence is. It's a bunch of things in a particular order, and we're going to be studying that and what the use of those are and the different types that we have. So first of all, we're looking at just general patterns, which is so important. I mean, that is like the very foundation of a lot of mathematics is finding and spotting patterns. Like the patterns we see like when solving like a quadratic equation, for example, or patterns when factorizing or things like that. Patterns in shapes, symmetries, that sort of thing, all over the place. So we're going to be looking at just general patterns first. We're going to see how that applies then to actual sequences of numbers, like a linear sequence, where you see that keyword linear again. We'll see how that relates to sequences. That's the main thing we're looking at really is linear sequences, but we're also going to look at geometric sequences, which are very similar but also very different. We're going to look at those similarities and differences, and that's it. So we've just got these three sections, not too much. So we look at patterns first, just general patterns, um, and say if we had something like this. So we're making various patterns out of these little sticks, and we might be so each one is numbered. We've got the first pattern, the second pattern, the third pattern, and we might want to see what relationship that has to the number of sticks that are used in that pattern. So you see the first one, there's 6, there's 9, and then 12 for the second and third. So you could just count those up. Um, so if we wanted to work out how many rods will make up the fifth tower, I mean we could draw it all out. Um, but say if we didn't want to, how would we do that? Well, we need to be able to spot the pattern that's going on. So you see from 6 to 9 to 12, you see how it's going up by 3 each time. Well, and we can see why that is because you see there's a new square being added to the bottom. So it's adding like 1, 2, 3 sticks that essentially adds a new square. Well, we could then find the fifth. So we've got the third tower. The fourth tower would be adding another 3. So 12 plus 3. The fifth tower would then be another 3 on top of that. So it'd be 12 plus 3, which comes up to 18. And if we drew them out, which we could easily do that as well, you could draw them out and then count up the number of sticks, and you'll see, yeah, it's 15 and then 18. But if we had, say, a scenario like this, okay, how many rods would make up the 50th tower? Now, this sort of way of doing it, just drawing it out is not going to be effective because that just take you forever. It's already getting quite tall and it's only 5. We're only up to the fifth pattern. So we need to find what is going on in like the general case. Now we can see it's going up by 3 each time. So we have the first one, which we can see is 3 plus 1 lot of 3. And then we have the second one, which is 3 plus 2 lots of 3. The third one, which is 3 plus 3 lots of 3. When you think of it like in those terms, we've now got like a general rule for finding each the number of sticks in each one. You can see it's basically 3 plus 3 lots of it's you know pattern number, 1, 2, 3, 4, 5. And so if we wanted to find the 50th one, it would be 3 plus 50 lots of 3. So, because you've got the first 3 that makes up the triangle, and then for each term you're basically adding one new square below it. So that's those 3 are making up the first triangle, and then you're putting 3 underneath each time to make a new square for the first, second, third, fourth term. And so the 50th term would be this. And so we could then just do that calculation. So that's the power of spotting a pattern like that. If we can see what the pattern is occurring, then we can project way into the future, like the 50th tower, what that would look like. We could also do this, say what would be the number of the tower that is made up of 234 rods. So say if we're given a tower that fits into this sequence and it has 234 rods, how many, like what would be the tower number? We could work that out by doing something like this, because okay, we know that the tower number essentially corresponds to the number of squares in this. So we take away 3, which is, making up the triangle at the top. And so we know we're adding 3 each time from there. So that remainder, if we divide that by 3, it will give us the term number, which is 71. So it's the 71st term in this sequence. So this is just kind of just thinking about it more logically. We're going to move on to like in the next section, looking at how to do this in a more rigorous way, actually using algebra and what's known as the nth term of a sequence. But this is kind of just the way we need to be thinking about it. Like what is going on, like from one term in the sequence to the next, and then how can we kind of broaden that, like extend that idea to just in general for a general term, and then that allows us to then project way further down the sequence. So this is an example of a linear sequence where you see it's just going up by a constant amount each time. But if we take, say, something like this, where we're creating these little pyramids, and we've got term number 1, 2, 3, and if we count up the number of blocks in each pyramid, you can see it's going 1, 3, 6. And say if we wanted to know how many blocks will be in the 6th tower, well, we could kind of follow the pattern. Like you see in that 3rd tower, we've got 1 plus 2 plus 3. If we start looking down the rows of the tower, so the first one is just 1. The second tower is 1 plus 2. The third tower is 1 plus 2 plus 3. And we could continue that on. The 6th tower would then be 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if we work all that out, it's going to come out to 21. And again, we could have just drawn this out. 4, 5, 6. These are the towers we're going to get. And we could count up all the blocks that make up those towers, and you see it comes up to 21. And this sequence is 1, 3, 6, 10, 15, 21. This is what's known as a triangular sequence because of this interpretation of it. These are triangle numbers, like how we've kind of seen square numbers and we've seen cube numbers. These are triangle numbers because you see when you interpret them like this, they form pyramids, triangles, and or triangular shape. It's not an actual triangle, is it? So again, what would we do if we wanted to look further down the road? Like what tower number will have 55 blocks? For something like this, we would have to continue following this pattern. So, we see for the 7th tower, it would be 28. For the 8th, it will be 36. For the 9th, it will be 45. And then for the 10th, it will be 55. And so we can see it's tower number 10 that would have 55 blocks in it. Just calculating out for each term. Could we come up with some kind of like formula similar to what we did before that would allow us to just calculate, directly what number that would be? We can, but that's a little bit beyond the foundation level mathematics. This is an example of a quadratic sequence, which is only taught in the higher level math. So we don't have to worry about that. You might have just more like physical patterns like this, where you see blocks being put together with simpler questions you might encounter. But in terms of actually coming up with like a formula that will calculate things for the nth term, which is what we're going to look at now, we only look at linear sequences and geometric, which we haven't come to yet. But let's look at linear sequences in more detail. So a linear sequence would be something like this. So we take away the pictures now of blocks or sticks or anything like that, and we're more looking at this in abstract. So we've just literally got a sequence of numbers here, and the key, we want to look at what is changing from one term to the next. Like, how is it changing? And if we look closely at this, you can see we're going up by 3 each time, and it's the same amount each time we're going up. And this is a hallmark of a linear sequence, is it will go up at the same rate each time. And the reason why we call it linear sequence is that we could generate like a function for the nth term, which will be a linear equation. That's why it's called a linear sequence. So how would we work out what that is? That tends to be one of the more challenging questions we can come across to do with sequences. It's actually find nth term. So the fact that we see it's going up by 3 each time, that sets what is known, the rate of change of the sequence. Now, how is it changing from one term to the next? Well, it's going up by 3. And that is essentially like akin to a gradient, like what we've seen with graphs. Remember, with a graph, like a gradient is basically for every one we go across, how much are we going up or down for that matter. It's the same thing here. As we go up by one, one term to the next, to the next, next, how much are we going up or down? You see, we're going up 3. So it's like a gradient. And so we know this is going to essentially be like 3n. You see up in the top right there, I've got the general equation for a linear equation that we've seen, like y equals mx plus c. So you could see it as like y being the value of a term and x being the term number. And so far we've got 3n. We know 3n is going to have that gradient of 3. And if we work out what that is for n equals 1, 2, 3, 4, so the first term, second term, third term, so on, you see we get 3, 6, 9, 12, 15. And so, yeah, it's going up by 3 each time. So great, it's going up by the same rate, but the numbers aren't actually matching. And it's because they're all off by some constant amount, that constant amount being the plus c. So, okay, what is that going to be? Well, we could just look at any term in the sequence, like the first one for simplicity. You see with 3n, the first term is 3, but we need the first term to be 5. So what we can do, just add 2, because we know we're just off by a constant amount right now. So if we add 2 to every term in that sequence, 3 becomes 5, 6 becomes 8, 9 becomes 11, and so on. You see now it matches the sequence, 5, 8, 11, 14, 17. So this here, 3n plus 2, would be our like you can see it like a generator function. This will generate more and more terms of the sequence. If we want to know what the nth term is, like the 100th term, we could just put in a value of n equals 100, and that little expression will then give us the value of that term. So that's what's really handy about this. So if we take an example, like what will be the value of the 87th term? Just pick a random number, 87th term. We can just plug that in. 3 times 87 plus 2, 263. So it's not like we have to write out this entire sequence, just keep add 3, add 3, add 3, add 3. It'll take forever. We now have this formula. We could work out the 87th term or the 1000th term or the millionth term. And all we've got to do is just plug it into that formula. We could also do things in reverse. So what is the number n, like the term number for the first term that has a value over 140? So we're looking for values that are going to be over 420. Sorry. So greater than 420 is basically like an inequality. What we're trying to find is basically the solution to this. 3n plus 2 is then the value of each of our terms. We want to find when does, for what value of n, like what term number is then going to be greater than 420. And so if we now solve this inequality in the same way we usually do, being mindful of when inequalities might flip, it shouldn't in this case. What we'll do is we'll get n is greater than 139.3 recurrent. I've just rounded it to one decimal place there. So, okay, is that then the solution? No, because this is really important for certain problems. So you need to be aware of the context that you're working in. So what n represents here is a term number in this sequence. So you've got the first term, second term, third term, so on. They're whole numbers. You can't have the 139.3rd term. That doesn't make any sense. We've got the 139th term, and then we've got the 140th term. Now, the 139th term is going to be a little bit too small. The 140th is going to be then over 420. So we can see that n would be greater than 139. So 140 onwards, basically. Strictly greater than 139. Or we could run it like this, where n is greater than or equal to 140. So when dealing with integer values like that, we could write it two slightly different ways, but the key is it needs to be from term 140 onwards. And how you write it, as long as it's communicating that information, that's what matters. Um, if you're ever unsure exactly, how you're going to write the inequalities, like sometimes it's good to actually just generate the 2 points around there. So we was at 139.3. So okay, let's look at term 139, term 140. We calculate them, and we'll see we've got 419 and 422. And so okay, now you can clearly see it's from term 140 onwards. So then you make sure you just write that correctly in your inequality, and then you'll be fine. So there you go. So that's why I often say to think of this like a function, like f of n, something like that, that's generate. Because what we're doing here is kind of like what we did before when we was looking at different types of equations, and functions in particular, where a function is basically it takes an input and it gives you an output. And sometimes, we're given an input and we want to calculate the output, or other times we're given the output and we're trying to work our way back to calculate the input. So it's a good way of viewing it, like here. So let's move on to a different sequence just to cement this idea. So we've got one like this. It looks a little bit different, but again, see how it's changing from one to the next. You see it's changing by a constant amount, but this time it's going down. So we're minusing 5 each time, or subtracting 5, I should say. Um, so that's the gradient. That's the rate of change of this sequence. It's for every one we're going across, we're going down 5. And so we know the equation for the nth term is going to be, it's going to have minus 5n plus some constant amount. So let's look at what minus 5n would produce first of all. That get, for n equals 1, 2, 3, 4, we get minus 5, minus 10, minus 15, so on. So we see we've got the correct rate of change. We're going down by 5 each time, but again, our values are off. So we need to add some constant value. In this case, it's going to be plus 16. Again, just look at that first term is normally the easiest thing to do. Minus 5. What do we need to add or subtract to that to get it to 11? Well, it's add in 16. So if we add 16 to all those terms, you see it gets to 11, 6, 1, minus 4, minus 9. So you see it now matches. So this is now our generator function for this sequence. Minus 5, f of n being minus 5n plus 16 would generate the nth term of this sequence. So now we can consider things like this, like what will be the value of the 23rd term? All we have to do is just stick in that value of 23 for n and calculate, and we get minus 99. Or you could get something like this where it asks you, does the value of minus 144 occur in this sequence? How would we work out something like that? Okay, what we do is we kind of assume that it does occur. So if it does occur, then there will be some value of n such that this equation is true. So what we do, you see here, we've just basically got a little linear equation. We just solve this and we find we get n equals 32. Therefore, it does occur in the sequence because it's the 32nd term, we're found here. So, but the thing is, when you've got a linear equation like this, it's always going to produce a solution. Like we know we can solve something like this. So when would it prove something is not a term? So this is going to be similar to before. Like say if we look at the value 200, like minus 251. Well, we do the same thing. Okay, so there should be a value of n such that this would equal minus 251. Well, we get the value of n equals 53.4. And again, like before, has to be an integer value. And so this implies that no, there is no term such that that will be minus 251. You've got something that maybe it goes to minus 248 and then it skips to minus 253 and continues like that. It skips over that value. So that's how we would prove something like that. Is you want to prove something to a term in the sequence, you kind of just assume it is, solve the equation to find out what term number it is, like what value of n basically. And if that value is not an integer, then it's basically saying that no, it's not going to occur in that sequence. Right. So that's pretty much everything we on linear sequences that you could be asked. And now we're looking at geometric sequences, which, like I said, it was similar but also different. And we'll see what I mean by that. Like, so say if we have a sequence like this, a very different looking sequence, you can see it's kind of growing fast. And if we look at how that's growing from one term to the next, you see it's +3, +6, +12, +24, +48. You might get to see that that's basically the sequence that we're beginning with, 3, 6, 12, 24, 48. Now, that's not always going to be the case in a geometric sequence. It is the case here. And the reason for that is because it's doubling each time. You see 3 doubles to 6, 6 doubles to 12, 12 doubles to 24. So it's, doubling something is like adding to itself, isn't it? So that's why we're getting something like that. So when you get something like this, instead think of it in terms of multiplication. And you see actually it's multiplying by 2 each time, multiplying by a constant amount as well. It's just going up by a factor of 2 every time. And so this is then an example of a geometric sequence. So it's not just adding a constant amount, it's multiplying by a constant amount. So those are the two you really need to look for. It's all you'll really get tested on, mostly linear sequences, but you might get something like this. So it's always going to be either going up by a constant amount each time, but it might be adding or multiplying. So the general form for a sequence like this, that the like generator function, like f of n, is going to be of this form, where a is the first term, r is then what's known as the ratio. It's basically the factor that you're going up each time, and then n is just the term number as usual. And you get n minus 1 because, say for the first term, we need this to equal to a, and so we have r to the power of, if it's the first term, n is 1, so r to the power of 1 minus 1, which is 0, so that r just disappears. R to the 0 is 1, and so then you've got a times 1, it just equals a. So that's good. So that makes a then the first term, which simplifies things. So that's why we have an n minus 1 and not just to the n instead. So for this, so what we need to do, we identify what that first term is, and we identify what is the common factor that's going up each time, which in this case is 2. And that allows us to then form this equation that will generate for the nth term. So we get 3 times 2 to the power n minus 1. And so now we could use that to calculate other terms. So what will be the value of the 7th term in this sequence? So we've already got the first 6. What will be the 7th? Well, we could always use that equation, and it will be 192. Or we could just do the 96 times 2 to move on to the next term. But you can see how we could use this, say, if we was trying to calculate much further ahead. But you see, yeah, these grow very rapidly. Now, say if we had a question like this, kind of like what we had before, where it was asking us to validate whether or not a term is in the sequence. So is the value 700 a term in this sequence? So how would we do that? Because normally we'd let this 3 times 2 to the n minus 1 equal to 700, and then try and solve that. Well, that is kind of, I mean, it depends on the precise circumstance. It's a bit beyond GCSE level math, certainly beyond foundation level. And so we couldn't really solve something like that. But we don't really need to. We can work this out in different ways, and particularly by looking at the factors of 700. So there's a few different ways, bottom line is this is not a term in the sequence. And there's a few different ways we can prove this is not a term in the sequence. So first of all, 700 is not a multiple of 192. Like, we know these terms, they're basically just doubling one term to the next, isn't it? So therefore, the next term is going to be double 192, and then you're doubling that again, double. So that means 700 would have to be a factor, like a multiple, sorry, of 192 in order for that to then be a term. And you can kind of see this is not going to be a term anyway. 192, you double that, it's going to be a bit below 400. You double that again, it's going to be a bit below 800. It's not going to quite hit 700. If you're not convinced by that, another way we could look at is looking by the fact that 700 has prime factors of 5 and 7. So what we could do is you could break down 700 using our factor tree that we've done before. And you see all the different factors that it's got. And we see it's going to have prime factors of 5 and 7. Now, if we look at this generator function that we have, 3 times 2 to the power n minus 1, you see the only prime factors it has is 3 and 2. It's basically 3 times by 2 some number of times. So the only prime factors it's going to have is 3 and 2. So if we get this number 700, well, where do these factors of 5 and 7 come from? We know they can't have factors of 5 and 7. So therefore, 700 can't be a term in this sequence. Or furthermore, we could just simply say that 700 is not divisible by 3 because we know we're starting from 3 and then we're doubling each time from there. So 700 it is a factor of it is a multiple of 2, but it's not a multiple of 3. And we can check that using like our basic divisibility rules. You remember all the way back onto our study of numbers. If the digits of a number add up to 3, add up to a multiple of 3, then the number itself is a multiple of 3. So 700, do 7 plus 0 plus 0 is 7. 7 is not divisible by 3. And so 700 is not divisible by 3. And but we know all the terms in this sequence must be divisible by 3 because they're all going to have that factor. So that's another way we could disprove it. So many ways we could disprove it there. And so you see similar kind of problems we could be faced with a geometric sequence, just using the fact that it's not adding each time, it's multiplying each time. And so we're going to be looking at factors like this. Is how we can then prove certain things. So that's about it. Let's just take a couple look of other types of geometric sequence you might come across. Just not other types, but changing the starting point and the ratio. So here you see we've got something that's going 12, 6, 3. Then you've got 3 over 2, 3 over 4, 3 over 8. You might be able to spot that that's basically dividing by 2 each time. But the general formula we have is more, it's working with multiplication. So we could think of this more in terms of multiplying by a half each time, which is the same thing as dividing by 2. And so then the general formula we have is going to be 12, the first term, multiplied by the common ratio of a half to the power of n minus 1. So here we go. We've got a nice formula for that one. And we could then answer, similar problems like what we had before. Or you could get something like this, which looks kind of strange. It looks like it's jumping around all over the place. You get something like this is a clear sign that you're probably working with a geometric sequence and not a linear one, because the linear one wouldn't do this. And those are the only two that we consider foundation math. So you look at what's the common factor. You see this happens when you're multiplying by a negative number. So you see here 2, 6, 18, 54. You can see it's basically going up by a factor of 3 each time. And the fact that it's flipping from positive to negative is a sign that you're multiplying by a negative number. If you're familiar with your you see the last term in that sequence. Ignore that one. That one's incorrect. The 96. It just stops at 162. So you see, yeah, that negative will cause it to flip back and forth because of if you multiply two negatives, it becomes positive. You multiply then a positive by then a negative again, it's going to go back to negative. You times that negative by another negative, it's going to go back to positive. You can see it's going to flip back and forth like that. And so, but we would get a similar equation like this: 2 times minus 3 to the n minus 1. And then again, we could answer various problems on that. So that's geometric sequences. So let's leave that there. Leave you with a interesting fact about compound interest. So we looked at compound interest before. That is very closely related to a geometric sequence. If you remember back to compound interest, it should be, seeming very similar. Like suppose we had an example like this, where we're investing £1,000 for 4% compound interest per year. Remember how that works? We'd do £1,000 times by 1.04, because that would mark a 4% increase, wouldn't it? And then we times it by 1.4 as many years that we're projecting into the future. So if it's going up 4% per year, we would the amount of money we would have after n number of years would be 1,000 times by 1.04 to the power of n minus 1. So you see that's basically a geometric sequence. And we could generate that sequence if we wanted to, take 1,000 and then just keep timesing it by 1.04 over and over again. That will keep getting our 4% increase. And if we plotted it, the value of our investment we've made over, say, 10 years like this, you see it'll go up like this, 1,000 to 1,480, essentially going up by about 50%, which is a decent little amount. But the key thing with compound interest is when you look very far into the future, like say if we do say 30 years into the future like this, you can start to see it's not just going up in a straight line, it's a curve. And not only is it curving, like it's going up, but it's the rate at which it's going up is getting steeper and steeper over time. And this is then the power of compound interest. Even like quite a small amount can then grow very quickly. Like this one has tripled in value over that time. And imagine if you invested a much bigger amount, you'd make a much bigger return. And if you went over a longer period of time, like a lot of people over many, many decades, they've saved money over their life and they get to like their older age, and they might have something where the rate at which it's going up is so fast, you can just live off the interest and you don't have to actually even invest anymore. That's something people do. So this is the importance of like a life skill of investing money and saving money wisely and at an early age. So then you can enjoy that compound interest over a long period of time as it builds up like this. Unfortunate thing is debt works in very much the same way, so that's why you've got to be very careful with debt. But yeah, so this sort of financial knowledge is very, very important for real life stuff, isn't it? And it relates very closely to geometric sequences. Right. So there we go. That's the end of sequences and the end of algebra for us. So we're going to be moving on to another very big topic next week, which is geometry, which is the study of shapes and spaces and distances and angles and all that sort of thing. So I will see you there for geometry.